Recall that this week has been all about the fundamental theorem of calculus. We've set up the structure of the fundamental theorem of calculus, where we integrate a derivative over a set by evaluating the function at the boundary of the set. This showed up in our original fundamental theorem of calculus, where the integral over some interval from a to b of f prime dx is f at b minus f at a. We're integrating the derivative f prime over the interval from a to b by evaluating the function f at the boundary of the interval, and that's just the points a and b. In vector calculus, we expanded the idea of the derivative by inventing this del operator, partial with respect to xi, plus partial with respect to yj, plus partial with respect to zk. We can apply the del operator to scalar functions and also to vector functions. It shows up just like multiplication. So with scalars, well, it just shows up like multiplication. We have del f, and that told us the gradient of f. When we apply the del operator, a vector, to a vector field, also a vector, since we're using multiplication, we had two options for how we did this: the dot product and the cross product. Presumably, these are some form of derivative, because the cross product and the dot product show up in fundamental theorems of calculus. In all three of the fundamental theorems of calculus, we've got the integral of del and some function over some set is equal to the function evaluated at the boundary of the set. In the case of the gradients, we integrate the gradient dot dr over some curve in a line integral. And we can do that by just evaluating the function at the endpoints. In Stokes' theorem, we're integrating the curl of the vector field dot dA over some surface S. Yesterday, we talked about how dA is some small normal vector to the surface. And we can calculate this, the integral of the curl dot dA over some surface, by evaluating the vector field at the boundary of the surface. So it fits that structure. Integral of a derivative over a set is a function at the boundary of the set. And then finally, in the divergence theorem, the integral over some solid of the divergence of f dv is the surface integral of the vector field dot dA over the surface of the solid. One of the interesting things that shows up when we're integrating vector fields rather than just scalar functions, when we're integrating vector fields, we can integrate a vector field over a curve or over a surface. Specifically, we're talking about vector fields in R3. You can tell we're talking about vector fields in R3 because we're talking about cross products. And that's like the only cross product that we have. But we can integrate our vector field over a curve or over a surface. Just like when we were talking about I forgot what I was about to say. We can integrate a vector field over a curve, a one-dimensional curve, or a two-dimensional surface. All right. Let's take a look at this calculation. Let's give an example vector field xzi plus xyzj minus y squared k. Find the curl and the divergence. We want to look at the three components of our vector field. F1, the I component is just xz. F2, the j component is xyz. And F3, the k component is minus y squared. We have to remember how to construct the curl. I goes with 1, so we're going to have F2 and F3. J goes with 2, so I'm going to have F1 and F3. And K goes with 3, so I'm going to have F1 and F2. I can only remember this by stepping down the function. So F3 minus F2, F3 minus F1, and F2 minus F1. So that means I have to remember that this comes from a cross product, which is a determinant, So I'm going to alternate signs. Specifically, this one here has to be negative. The J component has to be negative. But then I can just write 3, 2, 3, 1, 2, 1. Odd one out, start up, start at the top and go down. Then I just have to remember everything's all mixed up. I is also related to dx, the partial with respect to x. So that's not going to show up in the cross product. So 3 goes with y, 2 goes with z. Mix them up. Same thing with the j component. J goes with the partial with respect to y. So that one's not going to show up in the j component of the curl. So 3 goes with x, 1 goes with z. We cross them up. And finally, k goes with the partial with respect to z. But we're going to mix them up. So 2 partial of f2 dx minus partial of f1 dy. That just happens to be how I remember this. I don't know what would be best for you to remember this, or even how necessary that might be. It's kind of like remembering your trig functions. There are a lot of different ways to remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Some people are like, oh, heck, another hour of algebra, and some people are called so katoa. My personal favorite is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. It's a little bit wordy, but oh heck, another hour of algebra is annoying because you have to remember sine, cosine, tangent is the order. And I was taught SOHCAHTOA with a super racist bend, so I'm not going to do that one. So that's it. All right. So my personal favorites, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. I should make some kind of survey to find out what portion of the population that's been through trig, which mnemonic device they use. I'd have a fourth category for other. Then I could find out if someone does some kind of weird thing. Maybe they draw a picture. They have to draw a picture. You know what I mean? Anyway, that's all beside the point. We've got to remember how to calculate the curl. And that's how I remember it. I remember the odd thing out, everything's mixed up. It's from a determinant, so the middle one's got to be negative. So we just made our calculations. Here's F1, F2, and F3. I took my partials with respect to X, Y, and Z, and I put them together into the curl formula, hopefully successfully. Then for the divergence is del dot the vector field. So the partial F1 dx plus the partial F2 dy plus the partial F3 dz. Remember this, the dot product is a scalar product. So we're coming up with a scalar function. We're reminded of the fact that this is a scalar function by looking at the divergence theorem, where we integrate the divergence of f times dv. The curl of f must be a vector because in Stokes' theorem, we integrate the curl of f dot dA. In Stokes' theorem, we're using a dot product. So that means the curl must be a vector. In the divergence theorem, we're using multiplication. That means divergence must be some scalar. So here's the divergence of f. Z plus xz. Nice little scalar function, whereas the curl was a vector, still with our I, J, K. Any questions on the calculation? How's everybody? Okay. All right, So one thing we haven't talked about is how curl and divergence are some kind of differentiation. More than just mechanically. We can see there's some kind of operation with first partial derivatives all put together in vectors and in with vector fields and with scalar functions. But like with a lot of weird operations in math, there's some things that we don't do. For example, I don't make a vector by taking the partial f1 dxi and then partial f2 dx dyj and partial f3 dzk. Why don't we have that? Same kind of question like when we look at matrix multiplication. Why don't we just multiply the corresponding components? Why is this matrix multiplication some weird vector combination thing? Mainly it's because that wouldn't tell us anything useful. So that means we're at the point where we have to start talking about what these three things represent. We know what one of them represents. We know that the gradient is the direction of maximum increase for the function. So the gradient indicates the direction of the maximum increase. When I originally wrote this down, I was thinking I'll just write direction of maximum increase up here, right next, but that'd be like cramming it in between lines. So, dang. So it's the direction of the maximum increase of our function, the steepest path up the hill. The curl of a vector field is telling us how much rotation is going on in the vector field. So it'd be the direction and the magnitude of maximum rotation. And the divergence of F is how much expansion we have. Notice that for divergence, we're not going to be talking about direction because divergence is a scalar. So let's call it amount. These are all derivatives. So this is all stuff that's happening at a point. This is all stuff that's happening at a point. So if we're standing on a hill, at one point, there'll be one direction that shows us the steepest path up the hill. If we take a step in any direction on that hill, that vector could change because we talk about things that are continuously variable. That's what put us in calculus in the first place. wanted to see how things change when they're changing continuously. So these being all derivative things have to be all things that are happening at a point. For the gradients, we want to think about the direction of maximum increase. Imagine yourself standing on a hill. What is the steepest path up the hill at that point? Just like we talk about the derivative being the slope of the tangent line at a point. Slope of the tangent line on its own doesn't really represent anything. But when we say, well, but it comes with the implied at a point, because everything that's a derivative is happening at a point. Derivatives are local things. For the curl, we're looking at the direction of magnitude of maximum rotation. If we imagine the vector field being the airflow in this room, that's one of the things we set vector fields up to be: airflow in a room or the surface of water for a 2D one. But if we imagine the air flowing around this room, at any point, the air could be swirling. We can imagine the air swirling. The curl is telling us how much swirl is going on. Also, if we think about where cross product comes from, remember when we calculate cross product, so x cross y, we put our fingers of our right hand in the direction of x and curl them towards y, the short way. And then our thumb is pointing in the direction of the cross product. The cross product is perpendicular to two vectors that are factors. So if we imagine the air swirling around this room, the curl is going to be like our thumb as we measure how things are swirling. So at one point up here, that we could see how the air is swirling. If the air is swirling this way, we kind of like grab the air with our fingers and curl it in. And there's my thumb pointing in the direction of the curl. If the air was swirling the other way, then our cross product would face the other direction. And we'd see swirl going the opposite direction. So think about the curl as the direction and magnitude of maximum rotation. In that sense, it fits with our gradients. It's a direction of maximum change. For the gradient, maximum increase in value of the function. For the curl, maximum direction of magnitude of maximum rotation. Divergence is the amount of expansion at a point. So is our vector field expanding for positive divergence or contracting for negative divergence? Here are our short descriptions for our three derivatives that show up in the fundamental theorem of calculus. Questions? Whenever you're in a math class and the instructor's like, oh, any questions? There's actually not two answers. I know it seems like a yes/no question, right? There are questions or there aren't questions. But there's actually three. There's yes, there are questions, and there's two versions of no, there aren't any questions. So kind of at your first level, where everything makes sense, that's no questions, because this all makes sense. Then one step above that would be the yes. Yes, there are questions. Here are the things that I don't understand. And our highest level of not knowing the F is going on in math class is no questions, because I don't even know what to ask. So they kind of alternate. All right, there's like no, then yes, and then no. This is the first time we try to put these ideas into your head. Not gradients. That one's old. That's from like weeks ago. We're experts at gradient now, right? Right. And I know you're all thinking, you brought up trig earlier. We're not even experts in trig. I know some of you think you're experts in trig, but you're not. That's because you just haven't been in the game long enough. Do you know what I mean? At a certain point, it's just a function of time. But anyway, it's the first time we started thinking about curl and divergence, and I haven't even drawn any pictures. We've calculated curl and divergence for a vector field, but what does this vector field look like? What is this vector telling us? What is this scalar function telling us? We don't have enough information yet. This is the first time. This is the first time we've even started thinking about these things. So it's kind of hard to even formulate questions. There was a question in the chat. Where does this show up in the real world? Dude, we are not even anywhere near that point. We don't get to barely be thinking about something and then start looking for applications. From a certain point of view, we're talking about dot products and cross products. Or if we have applications of dot products and cross products, there we have applications of these surface integrals and line integrals, just like with integration. But we have this calculation and these ideas, and there's a big disconnect between this calculation and these ideas. This is normal. This is what we need to think about. So that's what we need to think about. I just want these ideas implanted so that you're thinking when you're walking around and there's swirling wind, you start trying to see the curl. Think about divergence. Think about curl. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.